Okay, we're going to begin looking at Unit 4, which is on exponential and logarithmic functions. Now, this is something you should have started a little bit in Algebra 2, talked a little bit about the basics of exponential and logarithmic functions. We're just going to expand on that, see some more advanced things we can do with these two types of functions. So, exponential and logarithmic functions all deal with things that have variables in the exponent. So, typically, we have our general exponential equation, which we say is some number raised to the x power. So if I just start taking, say, for example, 2 to different powers, 2 to the first, 2 to the second, 2 to the third, so then I can have this function that's basically 2 to the x. It's just an arbitrary number of how many 2's I'm going to multiply together. That's exponential. And so in the course of Algebra 2, we determined that there is this need for this function called a logarithmic function. So a logarithmic function, all it simply does is says, what power do you need to raise a base to get a certain number? So for example, if I said y equals b to the x, so I'm basically asking b to what power is going to give me y? Well, we call that a log. So this expression y equals b to the x, which is an exponential expression, will simplify to an equivalent statement in a log, which is x equals log base b of y. So these two statements are essentially saying the same thing. So if I have y equal 2 to the x, that is the exact same thing as saying, all right, I want to know basically what power do I have to raise 2 to get y. That is the definition of a log function. So we can rewrite this as log base 2 of y. So it's a rearrangement going from an exponential function to this logarithmic function. So when I see log base 2 of y equal x, I know that's saying 2 to what power is y. So we can use this relationship between exponential and logarithmic functions, kind of reviewing things we did before. So here are a couple different statements. This is what's called an exponential form, and we want to write in logarithmic form. So these are both true statements. So this says 2 to the third equals 8. So if I want to write this in log form, log would be base 2. So I'm essentially saying 2 to what power equals 8. So this would be log base 2 of 8 equals 3. Now this other one deals with this special number of e. If you don't remember e is a transcendental number similar to pi that is used in lots of applications in economics and science and lots of places like that. So we can use this as one of our bases. We'll use it a lot. So if I want to switch forms of this is log, and the base is whatever the base is here. It's log base e, which in a second we won't write it like that anymore, of 8 equals x. So an exponential, whatever the exponent is, it goes by itself. You get log of the base equals the input. Now when you have this log base e, we have a special log for that. We call it the natural log, which is just represented with ln. Whenever you see ln, that means it's a log with a base of e. The other log you'll see a lot is just a regular old log with no number underneath it. If you see a log with no number on it, we automatically default it to 10. So that's called a common log, log, and then the natural log has this magical base of e, this odd transcendental number that we'll use for lots of different things. So here's another way we can do it. If these are in log form, I want to turn them to exponential form. So this says log base 2 of 16 equals 4. So again, what this means 2 to the fourth power equals 16. Again, getting this rearrangement from logarithmic to exponential is very important. In the second one, we're saying the base 8 to what power is x? So it's 8 to the second power equals x. So you can see for both of these, whatever was inside the log is going by itself. And then the base to the thing on the other side of the equal sign. Just the reverse of what we did for the exponentials. So we'll use these log functions a lot. So it's pretty helpful to know what what the value of some of these log expressions are. So we're going to use this idea of switching between log and exponential form to find some values of some log equations. So this first one says log base 5 of 625. Now remember what a log says. A log, all a log is saying, it's saying the base to what power is the input. That's all a log is saying. So in this part, log base 5 of 625, essentially we're asking 5 to what power is 625. So 5 to what power is 625? It would be 5 to the 4th power, because 5 to the 4th is 625. So log base 5 of 625 is simply 4. Now, can you put this in calculators and get this value? Sure. And you can check it if you want. Desmos has a great log function, but if they come out nice, it's relatively easy to do. This one says log base 2 of 1/8. So this is essentially saying 2 to what power is 1/8. Now, because I have a whole number on the left and a fraction on the right, I'm pretty confident my log is going to be negative, because if I take a negative exponent, that means to flip the expression over. If you forget that from algebra, x to the minus 1 is 1 over x. So if you have a fraction, it's typically a negative exponent. And we say 2 to what power is 8? Well, it's 2 to the 3rd is 8. So 2 to the negative 3rd is 1/8. So log base 2 of 1/8 is simply negative 3. Same for the next one. It says log base 12 of 144. This is asking 12 to what power is 144. That's a pretty easy one. 12 to the 2nd is 144. So the log base 12 of 144 is simply 2. Lastly, we have log base 18 of 1. A little different one. So what we do this is we would say 18 to what power is 1. And this is another one of those rules you kind of have to remember. Anything to the 0 power is 1. So this is simply 0. Because anything to the 0 always gives me 1. So hopefully these are things you remember. This is pretty standard stuff to do in like Algebra 2. If not, hopefully this is pretty easy to find these without a calculator. Now, one of our biggest things we're going to try to do is solve equations in this unit with exponential and logarithmic properties. So the one way a lot of times you learn in Algebra 2 how to solve exponential equations is use what's called the exponential law. Really simple law that we can use. It simply states this. If b to the x equals b to the y. So if I have two bases to different powers in an equation, then I can simply say x equals y. So if I have the same base, I can simply set the exponent to equal. If I don't have the same base, then I have two choices. I either can't use this, or I have to figure out how I can make the bases match somehow. So if I look at this first question, it says 3 to the x plus 1 equals 81. Now these bases obviously don't match. I have 3 on the left and 81 on the right. So I'm going to try to rewrite 81 maybe with a base of 3. Well, 81 I know is 9 and 9, and 9s are both 3 and 3. So I can write 81 as 3 times 3 times 3 times 3. So I can rewrite 81 as 3 to the 4th. So if I replace this equation with that, well, now I have 3 to the x plus 1 equals 3 to the 4th. So again, now the bases match. That's a good thing. So now if the bases match, I can simply set the exponents equal. X plus 1 equals 4. Solve for x, real simple. X equals 3. If we look at the next one, it says 5 to the x plus 3 equals 1/5. So again, I don't really want to change the 5. 5 is 5. But I can change the 1/5. Remember, I said 1/5. When you have that, that's typically a negative exponent. So I can say 5 to the minus 1 is 1/5. Because the negative exponent just flips it. So if I go backwards, 1/5 is 5 to the negative 1. So I could turn this equation to 5x plus 3 equals 5 to the minus 1. Now I have the same base, so I can just simply drop it. X plus 3 equals negative 1. Subtract 3. X equal negative 4. Real straightforward. Again, the only trick is getting the bases together. If you can't get the bases to be the same, then we can't use this method, and we'll have to find other methods later on how to solve these exponential equations. So this last one, we have 5 to the x squared plus 8 equals 125x. Again, I got to think of the 125, think if I can change it, because I'm not changing 5 too much. Well, I know this is 5 and 25 is 5 and 5. So 125 is 5 times 5 times 5, so it's 5 to the third. So I can change this to 5 to the x squared plus 8 equals 5 to the 3x. So now the bases cancel, and I'll have an equation of x squared plus 8 equals 3x. So now if I bring this down, it is quadratic. So quadratic, I generally get everything on the same side and put it in the right order. So I'll just move that 3x to the other side. So I get x squared minus 3x equals 8. Now my first goal would obviously be able to factor this and see if it factors. And if it factors, just, solve for those factors. Unfortunately, this one does not factor. There are no numbers that multiply to 8 and add to negative 3. So I'm going to use quadratic formula. You could use complete the square, whatever method you like. So negative b plus or minus b squared, which would be 9, minus 4 times a, which is 1, times c, which is 8, all over 2a. So that's 3 plus or minus the square root of 9 minus 32, which is negative 23 over 2. But as you can see here, my solutions are going to be plus minus I root 23 over 2. So we obviously cannot have imaginary exponents. So this is simply going to have no solution. So there's no numbers I can plug in there to make them the same. All right, so the final thing I want to kind of review is something we also reviewed earlier this year when we talk about logarithmic and exponential graphs. So if we want to remember the graphs of exponential log functions, we can do it lots of ways. So I'm going to start with two functions that have the same base. We have 10 to the x, and remember, if log has no number, no base, we assume it's 10, unless it says ln, then it's e. So we have 10 to the x and log of x. So if I just want to pick some numbers for this exponential, maybe I pick negative 1 and 0 and 1 and 2. If I plug those into the function, well, 10 to the second power is 100, so that's pretty big. 10 to the first power is 10. 10 to the 0 power is 1. 10 to the negative 1 is interesting because remember, that's going to flip it, so that's 1 over 10, or 0.1. So what our graph looks like, just like we looked earlier in the year, we have 0, 1, we have 110 way up here, 1 1/10 right here. And so what it looks like is it'll look something like this. And it'll hug that axis, it actually does not touch it. So this is very interesting for this. So there's any x. You can plug in any x you want. So the domain is all real numbers, negative infinity to infinity. But the range, because you can never take a base to a power and get a negative number, because it kind of hugs that y-axis, the range of this function is 0 to infinity. So it's always numbers that are greater than 0. Nothing smaller than 0. or 0 can be applied. Okay. This has a y-intercept. It has a y-intercept of 0, 1. And it has an x-intercept of none. It never touches this x-axis. What we actually get is we get this asymptote. We get a horizontal asymptote at y equals 0. So remember from the rationals, we can have these horizontal asymptotes. So this actually has a horizontal asymptote at y equals 0. So that's horizontal in this case. Now, so that's what an exponential function looks like. Now, remember, a logarithmic is an inverse function, so it should look very similar, only in a little different area. Flip, some things get changed around, and we'll kind of see the similarities and differences when we do our logarithmic function. Now, if I'm graphing my logarithmic function, this is a little trickier. So I'm just going to put some points on here, and we'll see how we can get these points later on in the class. But what I'm going to do is I'm going to pick some very special points. I'm going to pick 10 for my x value. I'm going to pick 1 for my x value. And I know these are nice because if I do log of 10, it's saying 10 to what power is 10? Well, that would be 1. And if I say log of 1, it's saying 10 to what power is 1? Well, that's 0. So those are two key points. So 10, 1 is on my graph, and 1, 0 is on my graph. And I will tell you, and you could graph this, what happens if you remember with the log, it dies like this. So it basically dies way down there. So if you notice these two graphs, they look very similar. They are just in different areas. This one has a vertical asymptote at 0. So this domain, the domain of this, and for logs, you remember the log is always greater than 0. We talked about that in like section 2. So the domain is 0 to infinity. The range is negative infinity to infinity. In this case, there is no y-intercept, but there is an x-intercept. It's 1, 0. So the y-intercept, there's none. The x-intercept is at 1, 0. And the asymptote here is a vertical asymptote at x equals 0. So it's vertical. Now, if you just look at these two different graphs that are inverses, you see lots of cool stuff. One thing I'll point out is if I look at the line that goes like this, y equals x. These two graphs are basically mirror images over that line. And that was one of the big things that had to be true when you had inverse functions. They had to be symmetric about that line. You could also see in some of these properties I've done for domain and range, if you notice the domain of the exponential is the same as the range of the logarithmic, and the range of the exponential is the same as the domain of the logarithmic because they're inverses. You also can see it switches from a vertical to a horizontal asymptote, and the intercepts also switch. So all this is kind of because these are inverse functions. So when we start graphing exponentials and logarithmic functions, we'll a lot of times find their inverse function because it goes right along with it. Okay? So again, our goal in this chapter is to get a deeper understanding of how these graphs look, how they work, and to solve some of the more difficult exponential and logarithmic functions and see where they're used. Where can we apply this in different aspects of life? So if you have questions, please let me know on this section.